Hydrogen helium. Next row down, N equals 2. You got 2 rows at the top, the alkali metals, right, and the alkali earths. Then you go to the right-hand side, there's 6 of them. Transition metals. How many columns of transition metals?
10.
The transition metals.
10.
10. Those 2 columns down at the very bottom that we're not going to fool with. How many do you think?
14.
Yeah. 14. Yes. And we're going to start filling those things up. At least in the end, P. But the quantum theory puts together a system that helps explain the shape of the periodic table based on the electrons in the specific shells and subshells. And you can remember these numbers by using the periodic table. Remind you that the S has 2 electrons, or 2 columns in the main group on the left. The P has 6 electrons, which are those 6 columns on the right-hand side of the main group. And the D is the transition metals. The book has a little table called the Aufbau principle that shows how to fill this up. And I never liked it. It never made a lot of sense to me. So I'm going to show you how to use the periodic table to fill these subshells, starting from 1s and going up as high as you want. And I even posted that as a slide that I showed you 1s on the on Angel. And in 2 weeks, you're going to have a dry lab where you're going to be writing electron configurations. You might want to bring that with you. It'll help you immensely to write electron configurations. And it'll be very handy. But it starts, let me say that N equals 1 is the lowest, most stable, so that's where the first electrons go. And then you go to 2s, 2p, 3s, 3p. Everything seems to be following nicely. And then you get a funny thing. It goes, instead of going 3d, it goes to 4s. And we're going to see that in the periodic table. 1s. This number here is your principal quantum number. N equals 1, N equals 2, 3, 4. So 1s, 2 electrons. The 2s, 2 electrons. 3s, 2 electrons, 2 electrons. Over here, this is called the p block because there's 6 columns here, which represents the 6 electrons in those p subshells. So we go from 1s to 2s to 2p, then we jump down to sodium to 3s, across here to 3p, and notice the D's don't start yet.
Yeah.
This is our D block. They call it the D block transition. It goes from 3p to 4s, and then 3p. So it's like the D's are shifted down 1. You know, it's 4s, 3d, 5s, 4d, and down here it gets a little complicated in the S one. So we're going to show how you can write an electron configuration for any atom up to where? I guess here. We're going to stay out of it. Up to here. So the 6s would be strontium. Farad. This is a very handy guide for doing it. Very handy guide. Right, 2 electrons, 6 electrons, 10 electrons. S, P, and D. Where the F is 14. It's called the Aufbau principle. Starting from 1s and working your way up. Then there's another rule called the Pauli exclusion principle. Wolfgang Pauli did some calculations and shows that these electrons act like little spinning tops. They have some property called spin. And when you put them in a magnetic field, they'll tend to move in two different directions, depending upon which direction it's spinning. And so that's why we showed that when the two electrons are in the subshell, their spins have to be in the opposite directions. Their spins have to be in opposite directions. We're going to show as we fill our subshells, starting from 1s and working our way up, we got to show these in opposite directions. There's another rule, which I'm going to get to with these. It's called Hund's rule. And we're going to do that when we start filling up our P's and D's. And Hund's rule says, let's say we're going to do that 2P. We have to put 6 electrons in there. Well, the first one's going to go right here. It's going to go like that. The next one, we're not going to put it in there. We're going to put it in its own little subshell out here. Fill them like this. That's the second electron. Because each electron would be more stable if it had its own little subshell, right? And that's the third one. This is Hund's rule. This is how you fill a P or a D. Then to go back, you go back and fill them 4, 5, 6, 4. And that's how you fill them. We're going to do some more of these. Lots of steps. Hund's rule. So here's our configuration for lithium. There's 2 ways we can show this. One is called the electron configuration, and the other is called the orbital diagram. The orbital diagram uses the arrows. The electron configuration uses the little superscripts to tell you how many electrons. This is a little more informative, as we're going to see when we start going up, but this is also useful. So here's the electrons in lithium. Lithium is a alkali metal. What does it like? Very reactive. What does lithium like to do? Chemical reactivity is it wants to lose electrons. Or how many electrons do you want to lose? 1. Which one do you think it's going to lose? 2s. Right there. And when it does, what element has that configuration? Helium. Oh, gas. This is the power of the quantum theory. Quantum mechanics. Here's carbon. It's got 6 electrons. So it has 2 electrons here. 1s, that's our first one. Then the 2s, and if you use the periodic table to follow across, then we got to go to the 2p, and according to Hund's rule, we got to put those 2 electrons for carbon to get the 6 total in each in its little separate orbital.
They don't have to be going opposite directions?
No, they go in the same direction. We show them that way, going in the same direction. We're going to do some more here in a second. So there's carbon. Let's do nitrogen. Well, you got your periodic table. You can follow how many electrons in nitrogen? 7, right? Yeah. Then 7 for nitrogen and 8 for oxygen. And so it's going to be just like this. We'll start with the 1s, 2 electrons.
2s.
That's the top row, right? Then 2s,
And then
2 electrons.
P.
And we have 3 more. Right, so it's going to be 2p, 3. And there's our 7 electrons. And if we fill these, how are we going to do that? 2 electrons here. 1s. 2 electrons in the 2s. And then how do we fill the 2p for nitrogen?
3 of them?
3 of
Going
them.
up.
1, 2, 3. Like so.